Good morning, guys. Hope all are doing well. So ask your friends to join quickly. Okay, so today we will discuss on the closure on the transitive. So as yesterday we were discussing closure on the symmetric and the reflexive relation. So let's move on to the next discussion, that is the closure property on the transitive relation. So here also we consider let R be any relation on the given set. Okay, and we know that. So some of the properties we must know that R square, if you want, from given set R, then we will write it as R dot R. Means the relation R with R, we will obtain R square. And in generally, if you want Rn, so R to the power n will be equal to R to the power n minus 1 into R. That is Rn minus 1 dot R will give us the Rn. So in general, if I am talking about the whole, suppose R star, the relationship, the R star is nothing but the transitive closure. So this is nothing but, it is the union of all such Ri where my I is running from 1 to infinity. So where my R star will be the union of all the Ri's. Are you able to see the screen and are you able to listen both the sessions G and H?
Yes, ma'am.
Okay. So here, what we are doing is, we are doing, I'm going to explain this more accurately with the examples so that it will be more clear. So here, basically we will be given with one simple set and one simple relation. By using that relation, we can achieve n number of relations. We can achieve n number of relations. So here basically, whatever the R star I'm denoting, that will be my transitive closure. Okay, so some properties are there on the transitive closure, and even this property I'm going to help explain you with the help of example. So here, please remember R star, this is a transitive closure of a relation R. So R star is nothing but what? It is union of Ri, where I is running from 1 to infinity. What is Ri? If I is equal to 1, it is simply R. If I is equal to 2, then it is R2. How do you obtain R2? R2 is R dot R. How do you obtain R3? It is R square dot R, and so on and so forth. So all are interconnected. So all are interconnected. So when I obtain this R star, this is nothing but the transitive closure which is defined on the relation R. This is one of the property. Similarly, R be a relation on the set A with suppose n number of elements, then the transitive R will be equal to, please remember, the transitive R is equal to, it is R union R square union R to the power n, if it is containing n number of elements. What if it contains two numbers or three numbers? If it contains, say suppose the element A is containing three elements, then my transitive R will be simply R union R square union R cube. If it is containing two elements, it's simply R union R square. So what is R square here? It is R dot R. What is R cube? It is R square dot R. Am I clear up to these points? Both the sections?
Yes, ma'am.
Okay. So let's see some example and let us understand how do we go with these examples. So here, consider the following relation R on the given set A. So A is the given set 1, 2, 3. So now just looking at the example, see R is equal to A is equal to 1, 2, 3 means there are three elements present in A. And also they have defined R here. R is defined. So how do we go with R square then? We know that R square is R dot R and it is a transitive relation. So transitive relation means R dot R should contain, see, 1 is related to 2 and 2 is related to 3, means 1 should be related to 3. So this should be present in R square. So it's a transitive relation from R to R. Similarly, 2 is related to 3 and 3 is related to 3. Therefore, 2 is related to 3. Here it is. And 3 is related to 3 and 3 is again related to 3. So therefore, 3 is related to 3. So this is our R square or R dot R. Clear?
I'm going to re-explain it.
Yes. So R is given to us. From this R, we are supposed to obtain R square. So R square is nothing but R dot R. So transitive relation from R to R. We have to find out. So here you can see 1 is related to 2 and 2 is related to 3. That means transitive relation is from 1 to 3. That is one element. Similarly, 2 is related to 3 and 3 is related to 3. So therefore, 2 must be related to 3. That is another element which has to be there in R square. Similarly, 3 is related to 3. 3 is again related to 3. Hence, 3 is related to 3 is here. So this is how R dot R will be containing all the transitive relations from R to R. Am I clear?
Yes, ma'am.
Okay. So now R cube I am interested in. So R cube means nothing but what? R square dot R. R square dot R means already I have R square here and R here. So I have to go with. Let's see. R square is this. 1 is related to 3 and 3 is again related to 3. So here 1 is related to 3 and here in your R you can observe this is your R square and this is your R. 1 is related to 3, then 3 is related to 3. So 1 is related to 3 I am taking. So 2 is related to 3 and 3 is related to 3 here. 3 is related to 3 here. So therefore 2 is related to 3. Similarly, 3 is related to 3. 3 is again related to 3. Hence 3 is related to 3. So therefore this is our R cube. Following?
Yes, ma'am.
No confusion, right? So this has to be from R square to R. Here it is from R to R. If you want to go with R4, so it has to be what? Is it possible to go with R4, guys? As a transitive relation of R, it said you can calculate R4, but what is our transitive of R? Since how many elements are present here?
3.
3. So therefore, what should be our transitive of R? It is R union R square union R cube. Correct? Are you
Yes, ma'am.
following?
Yes, ma'am. Yes, ma'am.
Yeah. So this is your R, this is your R square, this is your R cube. Take the union of all. So 1, 2, 1, 2 I am writing. Then 2, 3 is here, 2, 3 is here, 2, 3 is here also. Write this. Then here you can see 1, 3. Here also 1, 3 because I am taking union. So 1, 3 I am writing. So 3, 3, 3, 3, 3, 3 everywhere it is. So 3, 3. So this is the union of all the 3. That's how we have got transitive of R. So what if it has containing one more element, say 4, then how many relations would have possible here? What would be this transitive of R, guys?
R union square, R union cube, and R union 3. Ma'am. It will be like 6.
R union, R square union, R cube union, R to the power 4.
4.
Okay, so like that. Fine. So now let's see. So this is all about the transitive closure. Okay, some more examples we will see at a stretch. So now let's come to the next important thing, equivalence relation. So am I clear up to that point, up to that example to everyone? Any questions?
Yes.
Yes, ma'am.
Okay. From G section, it's fine.
Yes, ma'am.
Okay. So now let's see what is the equivalence relation. So basically remember guys, equivalence relation is all about all the 3 relations which you have already studied. What are the 3 relations we have studied? Reflexive relation, symmetric relation and transitive relation. If any given set A, which is non-empty set, and there is a relation R, so that relation R, if it is all reflexive, it is symmetric and it is also transitive, if all the 3 properties are satisfying in one particular relation, then we call that relation as equivalence relation. So there should be a reflexive, there should be symmetric and there should be transitive. If all the three relations are satisfied, we call it as the equivalence relation. So reflexive means you know that if suppose there are three elements A, B, C, then A must be related to A, B must be related to B, and C must be related to C. So this has to be there. Then you know that if AB is there, BA must be there. If AC is there, then CA must be there. Then we call it as symmetric. And similarly, it has to be transitive. That is, if A is related to B and B is related to C, this implies A must be related to C. If these type of elements are also present here in the given set of relation, then we say that it is a equivalence relation. We say that it is a equivalence relation. So you can observe for any non-empty set A, there is a relation R on S is an equivalence relation. So if it has to be reflexive, it has to be symmetric, and it has to be transitive. Okay. So what are the properties? For every element A in the given set, A should be related to A. It has to be true for every element. And if A is related to B, there must be B is related to A. That is symmetric. If A is related to B and B is related to C, A must be related to C. That is transitive. If all these three conditions are satisfying in any given non-empty set of A where the relation is defined, then we call such relation as equivalence relation. We call it as equivalence relation. Am I clear?
Yes, ma'am.
Okay. So let's see some example. Consider the set L of lines and the set T of triangles in the Euclidean plane. I am talking about the Euclidean plane. The relation is parallel to, I am talking about the relation parallel to or identical to. Identical to means if line A is identical to line B, or I am talking about the line A is parallel to line B. So this particular relation on the given line in the Euclidean plane, this will be always equivalence relation. Always a equivalence relation. So for example, you can just observe any set of lines if they have given you. Okay, so in a Euclidean plane, if you are talking about, then you can take the lines and you can say that A is parallel to B and B is parallel to A, so symmetric. A is parallel to C, C is also parallel to A, that is again symmetric. Then if A is parallel to B and B is parallel to C, then A is parallel to C, then it is transitive. And here you can observe that every line in the Euclidean plane. So here for the, I'm just talking about, or you can see, I'm just using identical. So both I'm using. So if you're using this, then every line is identical to itself. So it is both reflexive, it is both transitive, and it is also having the symmetry. So hence, in the geometrical example, we can say they are the equivalence relations. Similarly, we have seen subset or equal to a set of inclusion. This is not an equivalence relation, because I say that if A is subset or equal to B, not necessarily B must be the same. Suppose A is equal to 1, 2 if I consider, and B is equal to say 1, 2, 3 I consider. Obviously A is subset of B, but what about B? So there is no symmetry. Since they are containing different number of elements, then there is no there is no reflexive, there is no transitive. So therefore they are not either this reflexive and transitive. You can see, for example, subset or equal to, if you say this is not an equivalence relation, so here if you see, symmetry will not go with. Symmetry will not go with. Though I have say A is equal to 1, 2, B is equal to 1, 2, 3, I may have some reflexive relations along with A, along with the B, but I will not get symmetry here. I will not get symmetry here. Hence, this would be an example for equivalence relation. Okay. So, here some example you have seen. Here they have given you A is equal to 1, 2, 3, 4, 5, and let R be the relation on the given set A such that this is defined in this way. X plus y element sum should be equal to 5. So what are the possible elements, guys, out of this? Sum must be 5. So I can take 1 and 4. I can take 2 and 3. I can take 3 and 2. So even I can take 4 and 1. These are the possible elements which we can take as a pair. So 1 4, 2 3, 4 1 and 3 2. So we can say that whether it is reflexive, no, because there is no 1 1, no 2 2, no 3 3, up to 5 5, there is no element. So therefore it is not reflexive. And is it symmetric? Yes. 1 4 is there, 4 1 is there, 2 3 is here, 3 2 is here. So this is symmetric. Is it, transitive? Is it transitive, guys? 1 is related to 4, 4 is related to 1. So 1 is related to 1 is missing. 1 is missing means over. So it is not transitive also. Correct? So this is there. R is anti-symmetric relation. R is, as far as this is concerned, it is not reflexive as A does not belongs to R. R is symmetric. R is not transitive. You can observe 1 4 belongs to R and 4 1 also belongs to R, but 1 1 does not belongs to R. Hence, if it is not transitive, one of the, there are two conditions which are not satisfying. Hence, it is not the equivalence relation. Are you following?
Yes, sir.
Okay. So this way you can just have some more examples by yourself. I have already uploaded the book in the Google Classroom. It is by Sham series. You will get some more examples there. You have to analyze the examples. Okay. So examples you see, go through the examples and try to solve some more examples. Okay. So now come to the next important concept, that is partial. Not consider the whole set. We will deal with this partial ordering relations by step. Let's see what we do here. There is a relation R and there is a set S. See, a relation R and there is a set S on a given set S. This relation is called as partial ordering or a partial order. Both is fine. Either we call it as partial ordering or we call it as partial order if R is reflexive, anti-symmetric and transitive. So it has to be reflexive, it has to be not symmetric, it is anti-symmetric and transitive. A set S together with the partial ordering R is called as partial ordered set. In short, it is called as poset. It is called as poset. So, what we are supposed to understand here, there is a set A on which we have a relation R, and this relation R must be how? So, this relation R must be reflexive, must be anti-symmetric. It has to be anti-symmetric and it must be transitive. So if all these three conditions are satisfying, then we say that the given relation along with the given set is the partial ordered set, or it is also called as poset. Let's see the example. Am I clear? There is no symmetry, but there is anti-symmetric. But there is reflexive and that way. In equivalence means transitive. When you're talking about the partial ordering, so instead of symmetric, we have the anti-symmetric. Okay, so that's what it has to be the importance of this partial ordering. So let's see what exactly this partial ordering relation talks about. So the partial ordering subset or equal to this of a set. Inclusion is a partial ordering on any collection of a set because it has three desired property. What are the three desired property? If A is subset or equal to A, so you know that every set is subset of itself. Therefore, reflexive holds true. Are you following, guys?
Yes, sir.
So the subset are equal to when I'm taking a set. So every set is a subset of itself. So therefore the reflexive condition holds true. And anti-symmetric means it says that if A is subset or equal to B and B is also subset or equal to A, then A must be equal to B. That's what anti-symmetric says. So that means if anything happens like this, if A is related to B and B is related to A, if this is happening only if when A is equal to B. So this is what is anti-symmetric is all about. So it looks like symmetry, but the condition here is A and B are equal. So this condition must be there. You know that this is possible in the subset only when the set A and set B are one another same. If set A is also 1, 2, 3, set B is also 1, 2, 3, automatically set A is subset or equal to B and B is subset or equal to A, and then they are one another same. Are you getting this point? This is
Yes, ma'am.
not possible when A and B are different. This is possible only when they are both are same. So this is the anti-symmetric condition. The last one is obviously if A is subset of B and B is subset of C, then A must be subset of C. This is the quite common thing. If A is equal to say 1, 2 and B is equal to say 1, 2, 3 and C is equal to say 1, 2, 3, 4. So this is subset of this and B is subset of this, then A must be subset of this. Are you observing?
Yes, ma'am.
So therefore, this inclusion condition is always a partial ordering relation. So this collection, we call it as the partial ordering relation. One of the example we quoted. Okay. So similarly, you can observe this less than or equal to on a set of real numbers. So this is again less than or equal to means you know that every element is less than or equal to itself. So obviously less than will not go with, but equal to, since equal to is also there, so this will go with the reflexive condition. Similarly, this you know that if I take 2 is less than or equal to 2, that means I have to take both elements one another same, then only I can go with the anti-symmetric. So here 2 is less than or equal to 2. This is 2 is also less than or equal to 2. It implies 2 is equal to 2. So this implies that anti-symmetric relation holds true. Similarly, transitive. If 1 is less than or equal to 2 or 2 is less than or equal to 3, then 1 must be less than or equal to 3. Okay. So hence, this less than or equal to 3, less than or equal to is also again partial ordering on the given set of real number. Are you following, guys?
Yes, ma'am.
Yeah. Now let me give an example here. So here if you see the relation A divides B. The relation A divides B. Whether it is a partial ordering on the given set of positive integers or not. Positive integers or the natural numbers, both are one another same. So however, A divides B is not a partial ordering on the set Z, okay? It is the relation on N. There is a difference. N is positive integers or you can say the natural numbers, both are one another same, okay? The same thing if I'm defining it on the integers, it won't be. Here it is partial order, but here it is not partial order. I will explain you how. You take here, every element divides itself, it is reflexive. Agree? A divides A, it is reflexive. Right?
Yes. Yes.
Yeah, please don't sleep. So similarly, 2 divides 2, I take another 2 divides 2. So that means what? 2 is equal to 2, then only it is anti-symmetric. So this is also possible. So 2 divides 4 and 4 divides 8. Then 2 also divides 8. It is transitive. So hence on the set of natural numbers or a positive integer, it is a partial ordering. But same thing, A divides B, if I take it on the set of integers, guys, just check. If A divides B and B divides A, does not imply A is equal to B. For example, 3 divides minus 3, I consider. You're taking, this is true, right? 3 divides minus 3. And also minus 3 is also dividing 3. But is it 3 and minus 3 are they same? According to anti-symmetric, they must be same, right?
They are not same.
Yes. So therefore, hence anti-symmetric property doesn't hold true in case of integers. Therefore, it will not form the partial ordering on the set of integers. But in the set of positive integers, it is an partial ordering relation. So therefore, please remember, whenever you are constructing an example, if you just change the set, then definitely you won't be able to, sometimes some properties will obey, sometimes on some sets the properties will not obey. Okay, so you have to be very specific and you have to be very careful when you're putting the examples. So some more examples also you can find it in that book which I have uploaded. Okay, so now let's see what is n-array relation. So this some of you might be using in the Python. So there, suppose you are doing the same task many times. Are you coming across with something called n array? You will do it for n times. Yes? If I'm doing it for 2 times, it is just to the power 2. If I am doing it for 3 times, it is ternary. Are you following?
Yes, ma'am.
Okay. So for any set S, a subset of the product set. The subset of product set means if I have S, I'm like, taking the product up to say n. So this S to the power n, it is called as n-array relation on the given set S. In particular, a subset of a set, say a subset of 3, I have missed here, a subset of 3, product of 3 sets, that is S to the power 3, it is called as ternary relation. It's called as ternary relation. So if you are going with n number of products of a same set, then we call it as n-array relation. Okay. So here, for example, let L be the line in a plane. Then betweenness. Betweenness means, like, suppose here I'm talking about A, B, C. There are 3 lines I'm talking about. So is a ternary relation on R on the points L, that is A, B, C belongs to R. So here B lies in between A and C on the line L. So for example, this is my line. So this is my point A, this is my point B, this is my point C. So here A, B, C, there are 3 points. So here you can see B is lying in between the points A and C. This betweenness which I am talking about, it is the ternary relation because there are 3 points in between these 2 points. I am interested in this relation. So this is, I'm just talking about in one plane. You can go with n number of planes. You can talk about any relation, n number of relations, which you might be repeating. Okay, so that we will consider as n-array relation. Just remember the definition, what exactly the n relation. Am I clear up to this point, guys?
Yes. Yes, ma'am.
G section?
And this is G section only.
G section only.
G section only. H section, people are sleeping. Yes? H section people, are you able to hear me? Yeah. See, my G section people are just telling me yes, and H section people are sleeping. Please don't do that. Now see this, guys. The equation x square is equal to y square plus z square, which is equal to 1, determines a ternary relation T on the set of R, that is real numbers, that is a triple xyz belongs to T if xyz satisfies this equation. So here this is a ternary relation between x and y and z. If x square is equal to y square plus z square, and this value if it is equal to 1, then only I say that x and y and z are related. So there is a ternary relation, which means this coordinates x, y, z is the coordinates of a point in R3. So R3 means what? It is what entity? In 2-dimensional, it is a circle. In 3-dimensional, what it is? Is it not sphere?
Sphere.
Yes. So here it is having 3 coordinates and these three coordinates are connected by means of this. That implies it is a sphere with center as 0, 0 and the radius as 1. So this is the ternary relation. Though you are studying the discrete mathematics, now you are connecting that to the geometry, analytical geometry. So like this, you can connect to the dots. As I was explaining you all when I was explaining you the linear algebra, though you are studying the linear algebra, you can connect to your different branches. The same way, here you are studying the discrete mathematics and you are connecting to the different modes. Okay, so this, if it comes, then you can do many things. Oh, and similarly, now I've given you guys some examples for practice problems. So do some problems. Okay, so this is one example here. This you can try, find out the Cartesian product out of this. So here I have given you simple how to find out if there are three different sets are given. How do you find out the Cartesian product of A, B, C? So with the help of diagram, I have explained you. Just observe here. First, see how many number of elements you have. So n of A is having 2 elements, n of B is having 3 elements, n of C is having 2 elements. So I started with the first main diagram. So this I started with A. This is my A. Here you can observe this is my A. So A is containing 1 and 2. The next, this 1A I'm connecting to B. So this B means X, Y, Z, and this 2 also I'm connecting to X, Y, Z. Are you able to see, guys?
Yes, ma'am.
Yeah. Now again, this every X is connected to C. That is 3, 4. Y is connected to 3, 4. Z is connected to 3, 4. So it's a tree diagram which will give you the relation. You can observe 1, X, 3. One relation. Are you observing? 1, X, 4. Another relation. So 1, Y, 3. Another relation. 1, Y, 4. Like that, you are making the relations. So this is a tree diagram which will explain you how the Cartesian product from A, B and C will occur. So this is also called as triplets, all ordered triplets. So if it is double you have, it is the just ordered pair. When you have this, it is called as ordered triplets, where every first element is coming from A, second element will be coming from B, and third element will be coming from C. Are you understanding the diagram, guys? How we got this?
Yes, ma'am.
So like this, you can take some different examples and you can try with a tree diagram. So example, also find out A cross B cross C. Okay, so do this for the same example, and this also you find out. Okay, and this also you try. So these practice problems I will create in the Google Classroom and I will post it. You just have to solve and you have to post it in the Google Classroom. So now see the fourth example. Same, given that A is given, B is given, let R be the following relation. Okay, so this already I have explained you. So this is a given relation, guys. We have to find out the matrix of relation. So matrix of relation means how do you do? I explained you. What is your relation from A to B? So you will write A here, that is 1, 2, 3, 4 here, and you will write here X, Y, Z, and then what do? You will see the relation. So 1. So then if there is no relation from 1 to X, then you will write it as 0. 1 to Z, there is relation, then you will write 1. Are you recalling it?
Yes, ma'am.
Yeah. So like that, you got to do it. I think I've already solved it. You just check. Then draw the arrow diagram. Arrow diagram means how do you do it? You will take this two sets, that is A and B, and you will write all the elements of A here, all the elements of B here. You will see, if suppose 1 is there and here say Y is there, 1 you will connect to Y by using the arrow mark. Like this, you will see all possible relations. Are you recalling?
Yes, ma'am.
And you know how do you find out the inverse of relation? Writing all this in the reverse order. If one Y is there, you will write in the inverse Y1. One Z is there, in the inverse you will write Z1, and so on and so forth. Getting, guys?
Yes.
I think you can solve this example by using that particular idea. Okay,
Yes,
so this example I have already solved. Just I think composition is left, that I will explain you because it is already 11:33. Okay, so now if anybody has any doubts, any questions, let me know. Meanwhile, I will take your attendance. Yes? Any questions from G section, S section? Is the speed is fine for both the sections?
Yes, ma'am.
Any doubts if you're having anything? And some people are facing difficulty in understanding the, if I'm not wrong, they're feeling difficulty in what? They're understanding, I think, the notation. So please, whenever if you're feeling difficulty,